Alright, welcome to 45-minute class. We just wasted several minutes doing something stupid. Mateo. Last class, we did a lot of things. So here's what we're going to do today. We're going to learn a new thing. It takes about half an hour, so we're going to spend about 10 minutes going over homework right now. Much of which was exciting and interesting. So here, I would like to go over briefly, extremely briefly, the Riemann Sums packet, because I thought that was kind of interesting. I asked you guys to finish that, yeah? Yep. I would also potentially, we could do one FTC AP problems. We could do, did I tell you to finish that, or just do like 1, 2, and 3 or something like that? 1, 2, and 3. So we could potentially do about one of those, or we could go over the Riemann Sums packet a little bit, or we could do the snow driveway problem, or we could go over some book work problems, or combinations. But we have to stop in time so we can learn a new thing.
What is in time?
It's going to take about 30 minutes, I would say. So really like 10 minutes, 10, 15 minutes. Yeah. Sandy, request? Interesting. Okay, yeah, book and an AP problem. Yeah, we can probably do that. So some of the stuff from the textbook, first of all, there was that one like really brief thing I thought. I think I'm going to do like 4 problems from a certain page. Do we need to talk about that at all? It was like page 329? Yeah, that's right. 329, looks like 105 or whatever, right? So it said, take the integral number 105, said take the integral from 0 to x cubed of sine of t squared, is that correct? Yeah. Sine of t squared dt, and then differentiate it with respect to x. I taught you how to do this last class, or we discussed this last class, right? Stephen, what do you do? Did you do this? Problem.
I differentiate and
105?
Yeah.
This is 105? Page 329?
Yeah. Oh, so then yeah, that's like if you put in x cubed for t squared, and then like you get sine x cubed squared, that squared, and then back inside would be times 3x squared.
Yeah. That's it. Questions? Eric, questions? It's basically just a chain rule. If you get it, you get it. Okay, cool. How about 110? 110 was an interesting problem. I know we talked about, we did 109 like all together. 110 says, it was basically just another example of one of these problems which said find the distance traveled over the interval 0, 5. And the function was t minus 1, t minus 3 squared. Is that correct? Did you guys do this problem? Oh, yeah. So, and the directions were, if this is a position function, find the distance traveled on the interval 0, 5. Well, one way to do it is we can differentiate to get the velocity function. So I'll do the product rule. Do the first times the second. So it's t minus 3 squared, first times second, plus the first times the derivative of the second. So that would be 2 t minus 3. And then if I factor out a t minus 3, I get t minus 3 plus 2t minus 2. I think that's good. So that's t minus 3 times 3t minus 5, which tells me that my velocity on the interval 0, 5 looks like, well, there's a change at 5/3 and there's a change at 3. And it's quadratic, so my velocity is going to be positive, negative, positive. So I'm going to be moving to the right on the interval 0, 5/3. We're going to be moving to the left on the interval 5/3, 3, and we're moving to the right on the interval 3 and 2, 5. Everybody okay with this? Okay, good. So when it comes to finding the distance, if I want to find the distance traveled, I have 2 ways to do it. I can do, probably the easiest way is not to do any integrals at all, right? If I want to know the distance traveled, explain what I should do, like in using language. Shimon? Is that a hand? You're just scratching your head. I'm looking at you and saying, what's it mean?
Take x of 5 minus x of 0, except when it's like negative, make it positive.
wait, hold on. If I just do x of 5 minus x of 0, what is that going to give me?
Or like except when it's like less than 1, wait, or greater than 1, then like minus, change that.
I'll accept inarticulate responses, but I literally have no idea what you're talking about. Wait, what is x of 5 minus x of 0? First of all, just like what is that?
Like
Or like what's the meaning of that? Everyone.
Displacement.
Yeah, this is just a displacement, right? This is just the change. This would just be the change in position, on the interval 0, 5. But that's like not what I want, right? I mean, that's correct, but this is not what I'm interested in. What I'm interested in is the distance traveled, because think about it, I'm going to move into the right, then I'm going to move into the left, then I'm going to move into the right again. So in order to find the total distance traveled, I have to split it up into the interval. Did you guys do this problem? This is supposed to be like easy, because we did one like this already. Yeah, so what do you actually do?
It's like the area, so like intervals from 0 to 5/3 and then 5, but then minus 5/3 to 3 because that's like negative. Yeah, basically the speed for the absolute value, right?
Yeah, okay, so that's the one way of doing it. Yeah, you could say here's 5/3, here's 3, and here's 5. When I plug 5 into position, I'm going to get 4 times 4, so I get 16. No, that's not what I mean. I want to plug into speed. If I plug 5 in here, I get 10 times 2, I get 20. So my velocity is 20 when t is 5. My velocity is 0 at 5/3, and it's also 0 at 3. And let's see, when I plug in 0 into velocity, I get 15. So I claim that my velocity function looks like this, yeah? If that's what velocities looks like, then then basically what I want to do is I want to add up that area, and that area, and that area. But I don't want to just take the integral from 0 to 5, because the integral from 0 to 5 is going to give you the displacement, not the distance traveled. This is the fundamental concept. You got this? Okay, so what do? You have two options basically. You can either split it up into 3 separate integrals, which is what he seems to be talking about. That's what you mean, right? Yeah, you could take if I want this area, then I could take the integral from 0 to 5/3 of the velocity, which is going to give me a positive number. And then if I want this integral, this will be the integral from 5/3 to 3 of the velocity. But that is going to give me a negative number, consistent with the fact that my change of position is negative. So what I need to do is take this integral and subtract this integral, knowing that it is going to be negative. Does this make sense? And then finally, I add in the area of this, which is just the integral from 3 to 5 of the velocity. What amounts to the same thing is, since you have the position function already there for you, you could also just do, like, if you want that, you could just do x of 5/3 minus x of 0. That just will be that area, right? In other words, you're finding the displacement on this interval in which I've been moving all to the right, and then you take the displacement on the interval in which I've been moving all to the left. But as that displacement is going to be negative, I subtract it, and then I add the displacement. Is everyone cool with this? This is like one of the fundamental ideas of integration. All right, so that was supposed to take 1 minute, but you guys are looking at me weird. There are a couple other homework problems on from the textbook, right? Should we do like one? Final answer was like something weird, like I can't remember. 27.30.3 or something like that. Is that right? Yeah. 739 over 27. Yeah, I think that's right. Yeah, so it's like 27 and 10/27ths. Yeah, that's right. Raise your hand if you got this answer. That was an even problem. Like 2 people in the entire class got that number? What happened to the rest of you?
No, I did the
I
same.
made
I thought I
a
calculating
mistake
it.
somewhere when I was calculating that.
I have a question.
Yes.
Why wouldn't you take when x of t is negative, why wouldn't you take like the absolute value of t?
That is what you're doing, it's just like you're making.
You're
putting
taking
negative
the
signs.
absolute value of the derivative. What the book says to do is to take the position function, differentiate it, which is velocity, which is what we did, and then take the absolute value of that, which is speed. This is another way of thinking about it. And then you can integrate the speed from 0 to 5. So if you type that into your calculator, if you type the integral from 0 to 5 of the absolute value of this function into your calculator, you should also get 27 and 10/27s. If you wanted to actually do this by hand, you would have to basically do what I did here, which is to take this and split it up into the 3 pieces. Yeah, there's like sort of 3 different ways of thinking about it. You can take the positive integral under the velocity curve, and then take the negative area under the velocity curve and like flip the sign so that it all becomes positive. Or you could just construct the speed function, which is after all just the absolute value of velocity, and then take the straight integral. Or you could just anti-differentiate, get the position function, well in this case they gave it to you initially, and then just do this. But this is actually, via the fundamental theorem of calculus, this is exactly what you are doing when you are doing the integrals. You guys with me? It's like all supposed to come together. Okay, let's do like one more, we'll just like do like 1 or 2 more homework problems. I also gave you problems from like 359, was it?
Yeah.
Page
75.
359, let's just do like 1 or 2. 75 you want to do? Is that what you said?
Yeah.
75? Yeah, 75 assumes that you know how to anti-differentiate secant. So it says find the area of the region bounded by the graphs of these equations. So this is y equals 2 secant pi over 6x, and also x equals 0, and also y equals 0, and also x equals 2. Okay, so if you go to graph this function, when you plug in 0, secant of 0 is 1, so this starts at 2, and then by the time I get to 2, that's secant pi over 3, secant pi over 3 is a half, so this is like 1. And I think it's going to be like positive on the whole interval. Yes?
When it says something is bounded by y equals 0, does that mean it has to be greater than 0? Or what?
They're just saying, well, this is actually what we're going to do today, but they're just saying take the line x equals 0, which is that line, the line y equals 0, which is that line, and the line x equals 2, which is that line, and the curve, and the region bounded, so it's just the area of the curve. From x equals 0 to x equals 2. Yes?
If they give you like y equals -1, would you have to like calculate?
This is what we're going to do like today. This is actually like today's topic. So anyway, but for this case it's easy, right?
Yeah.
Yeah. So this is just the integral for, I mean it's not, the integral's not necessarily easy, but what they're talking about is relatively easy. So this is 2 secant pi over 6x dx, so now it just comes down to like, can you do this integral basically? Answer, maybe. If I let u be pi over 6x, then du is just like pi over 6 dx. So I need there to be a pi over 6 in there, so I do that and I undo the damage of the 6 over pi. So then this becomes 12 over pi, and then this is still 0, but this is now pi over 3, yeah? The 2 I took out, and so this is really just secant u du. Okay, now, I don't know if you guys know how to anti-differentiate secant, but we did learn it probably, and it was on like a review worksheet, and it's just like in the book and stuff, so it's just like the thing to know. And it is ln secant plus tan. ln absolute value secant u plus tan u, and that's just evaluated at pi over 3 and 0.
That's not even our
What?
No, it's like, I wouldn't remember it.
Yeah, you do that thing where you do this.
Oh, yeah. It's
That
oh, yeah,
thing.
that was the one that we kept complaining about.
Yep,
Yeah.
yep. Cool. So, the final answer is that this is 12 over pi times ln of the absolute value of secant pi over 3 is 2, right? Yeah. This is 2 plus tan of pi over 3 is root 3 minus ln of secant of 0 is 1 and tan of 0 is 0. And also ln of 1 is 0. So this whole thing is just 12 over pi times the natural log of 2 plus root 3. Beautiful number. What's up?
I got that, but I don't think it says that.
Yeah, it does.
It does? Okay.
Usually says it does. You sure about that? Okay, cool. All right, good. Can I have this homework? How you guys doing on these intervals? All right, good. Can we have homework? Let's turn it in right here. How much time do you have left in this class? Oh, like no time. Wait.
25 minutes.
25 minutes. That's not exactly enough time, but sort of will be, I guess. So.
Richard told me, he's like, I don't know what happened.
What is your password?
Well, normally it's like a
All right, so Cindy, we're done with this unit on integration. And what have we learned in this unit on integration? A lot of things. Specifically, we learned how to find the area under a curve. We learned all about the fundamental theorem of calculus. Yeah, just finish that text, whatever, you know. It's not like the middle of math class or anything. And we learned how to find the distance displacement. We learned all about the net change theorem and how we can solve all kinds of problems, like figuring out how much a child grows, populations of honeybees, how much oil is leaked from a well, gravel processing plants, all kinds of problems now are solved via fundamental theorem of calculus. We understand accumulator functions. We know how to do, what's it called? I was going to say something, I can't remember. Average value of a function, etc., etc. We're going to have a big test on this. It is going to be next week, Thursday. Because I think I see you guys on Tuesday, is that correct? Yeah, so good. All right, so now we are moving to the last unit of the year, which is really like a mini unit, because it's only like 3 classes worth. And we might not have a test on this unit, but we might have like a little tiny one, or maybe there's like a big quiz or something. But the last unit is called Applications of Integration. And we're going to do a little bit of this now, and it is also going to be the first thing that you do in Analysis 1B. So it's kind of a unit next year. So it's kind of a unit that's sort of spread over the summer in some ways. So, applications of integration. There are many, many applications of integration. And we had a conversation, or at least I think we did, on the fundamental theorem of calculus day about what integration really means. What does integration really mean to you on some deep level, Stephen?
Well, I mean, it is just like the area under.
It is just like the area under the curve. Can I get another answer? Besides being just the area under the curve. Yeah, Emma. It turns out that anti-differentiation assists you in doing integrals, but I still wouldn't have to say that that's what an integral is. An integral is a number, after all. It's like the total change in position. Yeah, but more generally, yeah. You're going to say that. What else? What else is integration besides just the area under the curve? There's like a deeper answer. Okay. All right. I'm going to tell you. I thought we talked about this. Even integration is the process of splitting up, of adding up an infinite number of infinitely small things. Anytime you find yourself adding up an infinite number of infinitely small things, you're doing integration. The main thing thus far that we have done with integration is use it to find the area under the curve. And that's actually what we're going to do today. But coming up in this unit is us using the concept of integration to find all kinds of things. We don't; those infinitely small things don't have to be rectangles. They could be volumes. They could be arc lengths. They could be, as especially you're going to do next year in Analysis 1B, you can add up an infinite number of infinitely small amounts of work in the physics sense, and figure out the total work that's done by an object. So there's tons of applications. So this is like a little mini unit on this. All right, today is not really a new concept per se. It is just new techniques to solve an old style of problems. We're going to talk about the area between two curves, and then the homework assignment on this topic is pretty difficult. And then next week we're going to learn how to find the volumes of things as they're rotated around certain axes. It's really, really cool. So this last unit is kind of chill, but it doesn't make it exactly easy. All right, number one, let's do it. please read the problem and make yourself a large, neat, detailed, high-quality picture. Yeah, how'd you know? Also, we have 20 minutes to do a 35-minute lecture, so we're going to go really fast.
Wow, that doesn't sound fun at all.
We should have. Yep, too late, I guess. Make a lot of mistakes. That was one of them. I don't know. I thought, was that worth doing? Or not really? So. You'll be fine. We can do this. We have 4 problems to do in 20 minutes. Should be fine. No, stop. I'm not doing this. This now. I'm gonna hand you some. We're doing this other thing. Guys, help us out. Yep.
Sorry, we let you down.
So, step 1, make yourself a really neat graph of sine and secant squared on the interval from 0 to 5/4.
0 to what?
5/4.
Oh, no.
So, sine kind of looks like that, right? It starts at 0 and goes up to √2/2. What does secant squared look like? Rohan, using what we know about secant squared, it's like secant looks like this, right? On the interval from -5/2 to 5/2, yeah? So Rohan, if you square that, what does it look like?
Like that.
Yeah, it kind of looks like that, right? Because if you square things which are bigger than 1, then they're just going to get like even bigger. You probably couldn't even tell the difference between secant and secant squared just without an accurate graph. Alright, so if I want to graph secant squared, when I plug in 0, I get 1, and by the time I get to pi/4, what is secant squared? I mean, it's 2, right? Because secant of pi/4 is 1 over √2, or sorry, secant of pi/4 is just √2. So secant squared is going to be 2. Alright, so after using the full range of my pre-calculus skills, I have made a beautiful, neat, high-quality, detailed graph of both sine and secant on the intervals 0 to pi/4.
Secant squared.
Secant squared, sorry. Some crap like that. Okay, so step 1 is to make a really nice big picture and to figure out what region we are actually trying to find the area of. But shade, please, lightly the region that we are trying to find the area of. It's the region between sine, secant squared, it just says from x equals 0 to 5/4. So I guess it's just like this, right? Okay. Do you have some idea about how to find the area of that region? Integrals. Yeah, Laura says, duh, I can do this no problem. I just want the area under secant squared minus the area under sine. Alright, that's totally fine and will work just fine, but I would like to encourage you to do it a kind of a little bit more nice way, which is instead of taking all these rectangles and then subtracting all these rectangles, why don't we just do it all at once with a single rectangle? So really what we're doing is we're taking the interval from 0 to pi/4, we're partitioning it up into a bunch of subintervals, and the ith rectangle on this interval is just going to have a height. So if that's like x sub I star, then I'm just constructing the rectangle of width delta x and height the difference in the y values of the two functions. Right? So the height of that rectangle for a particular x sub I star is just going to be, secant squared x sub I star minus sine x sub I star. And thus I can sort of think of that region as split up into a bunch of rectangles, each of which has a height which the difference in the y values for the particular sample point. Very cool? But so what does this turn out to be? Well, I'm just really like adding up all those guys. So this is just the integral from 0 to pi over 4 of secant squared x minus sine x dx. And of course, by the fact that you can split up an integral into two, it's the same thing as what Laura said, right? But it's just thinking of it a little bit differently. All right, do that problem, get an answer, go on to the next problem immediately. Cool. Keep going, keep going. Did you get root 2 over 2? Awesome. Okay, next problem. I always do it like pi over 4 minus 0. Some people like to split it up. Okay, so this next problem says find the area of the region in between 2 minus x squared and y equals negative x. So for this, I need to draw a picture because otherwise I have no idea what's going on. So let's do that. Line situation. Okay, so you guys have it up, upside down parabola, and the line y equals negative x. All right, so it appears that the region they must be talking about is like this one, right? Those two curves like enclose a region. So the first thing to do is to like carefully read the question, draw a picture, reread it again to make sure that the region that they're talking about is the region that you found.
Yeah.
All right, so I'm feeling pretty good. How can we find the area of that region? Actually, even before we start to figure out how to find the area, let's make sure we even understand this region. For example, what makes this problem a little different than the previous problem? Besides, they intersect. So we need to know where they intersect, right? Because I don't even know where to like begin my partition. Exactly. Thank you. So where do these two curves intersect? You got to do a little bit of algebra 1.
Oh, yeah.
Really? What do you like?
Not many things. I mean, Beyonce is a standard. That's like the only thing I like. Oh yeah, geometry was that.
Okay, so my algebra 1 tells me that these curves intersect at -1, 1, and also at 2, -2. Is that what you got? So yes, good. All right. So we need to find the. Okay, and now maybe you see the sort of beauty of thinking about decomposing it this way, right? Because Laura, if we were trying to do it like what you said, you would now get stuck into some like tangled web of like weirdness regarding like negatives and crap like that. Because the area under the parabola would now be like some mixture of positive things and negative things. It would just give you like confusing answers. And like same with the line, right? So you don't want to do that. You just want to think about the region as like a single chunk, which we're going to be slicing up. Shivani, you cool? Stop zoning out. All right. So we're taking the interval from -1 to 2, and that's what we're partitioning. And the key to doing these problems correctly, in my opinion, is to draw yourself a representative rectangle, which is why I insist that you do that. And a representative rectangle for any particular area is a rectangle which, like, which just represents the region, in the sense that the height of the rectangle is always determined by the y value of the parabola, and the bottom y value of the rectangle is determined by the y value of the line. So Scott, some people have some trouble like getting over this, right? Like, if you want to know the height of this rectangle, it's just the difference in the y values. Regardless of whether those y values are both positive, or one's positive and one's negative, or they're both negative, if you just subtract the two numbers, then you always get the difference between them. Cool? Okay, so what is the integral which will solve this problem?
Integral from -1 to 2 minus x squared.
So we're just adding up an infinite number of rectangles. I mean, if we want to get like serious about it, what we're really doing is we're taking the limit as n goes to infinity of the sum of a bunch of rectangles, and each rectangle has height, parabola, so like 2 minus x sub I star squared, minus the other guy, negative x sub I star. And then you're taking that being the height of the ith rectangle, then that gets multiplied by delta x. Most people skip that step, but I feel like it is kind of important to think about what's really going on here. We really are taking a whole bunch, an infinite number of things which are that tall and that wide, adding them all up, taking the limit as n goes to infinity. So yeah, we can do this with an integral. It's just going to be the integral from -1 to 2, just as I was saying, of 2 minus x squared minus negative x. And we multiply by dx. Cool. So do that integral, and then go to the next problem.